Interference is a wave property that light exhibits when it goes through two slits in some medium. And to talk about interference, we need to have some important ideas under our belts. The first one is we're going to simplify things by talking about what we call coherent light, where all the light waves are in phase. And this would be usually a laser light or a single light. Another thing to remember is what interference really is. Constructive and destructive interference are two different types of interference. And constructive interference happens when peaks match up with peaks and trough matches up with troughs, and so you get a increase in the amplitude of the wave. Destructive interference is when the waves cancel, so the peak meets up with the trough. So in double slit interference, you have some sort of a card or barrier that has two slits in it. And when the light hits those two slits, it actually creates two new sources of light. And from those sources, the light bends around, and the waves are diffracted, and those diffracted waves overlap. And what you get is constructive and destructive interference of the two waves, and it'll show up as light and dark spots on a screen. So we have some math to deal with double slit interference. In the first equation, you've got delta L, which is the difference in the distance the two waves travel, and you've got D, which is how far apart the slits are, and then sine theta is the angle that the light makes when it goes through the slit. For constructive interference, you've got whole wavelengths, and destructive interference, you've got an equation with half wavelengths, and hopefully that makes sense because the half wavelengths, the two waves are out of phase with each other. And then the last one is if you want to find how far away a fringe, which is one of those bright spots, is from the center to whichever fringe you're headed for, you would use that fourth equation. Now, if you look at this illustration, it kind of shows you what the idea of m is, and you see the m's in the equations. That's just a number assigned to the fringe. So the brightest center fringe is 0, and then you have m is 1, m is 2, all the way out. Now, those are maximums. The minimums are in between. So where that destructive interference has occurred, you get those dark lines. And so the dark line, the one on either side of 0 is actually 1. And then you have 2. So count them like that. There is no 0th minimum. One thing to note is that the closer the slits are, the more the bright spots spread. And that kind of matches the idea that wave effects are most noticeable when light encounters small objects that have size similar to the wavelength. So here's an example problem. Asks you to calculate the wavelength of light that has a third minimum, so we're talking about the dark spot, at an angle of 30 degrees when going through double slits separated by 3 micrometers. You have to pay attention to the units. So the unknown is the wavelength. Our angle is 30. Our m is 2 because we're talking about the third minimum, and it is right after number 2. And then our d, our distance between the slits, is 3 micrometers. So this is destructive interference because we're talking about a minimum, so we're going to use the equation that has m plus a half in it, plug everything in, and it works out to be 600 nanometers. So you can have more than 2 slits. You can have 3, you can have 4, you can have a whole bunch, and when you get a whole bunch, you end up with a diffraction grating. But one of the things to note about it is that the total energy, if you're using the same light source, is going to remain the same no matter which number of slits you have. And when you increase the number of slits, it causes a few things. It's going to cause you to have more bright and dark fringes. You can see that in the illustration, and they seem to be more defined, so that you get narrow bright fringes that show up in between, and you get secondary maximas, so you get these little thin bright lines in between the very bright thick lines. So one of the cool things about light, and you probably noticed this from when you were a smaller kid, that bubbles have colors on them and oil slicks have colors in them. And so this is why it's called thin film interference. The thin films have a thickness that's on the same order of magnitude as the wavelength of light. And this causes us to see different colors because some of the light is reflected off the top surface and then some of it refracts and comes back to our eyes and has a longer path than the other reflected light from the first surface. So when the light comes in and bounces off the surface of the top of it, let's say a bubble, it can either stay in phase or invert. And how it's going to decide whether or not it's going to stay in phase or invert is by the indexes of refraction. If the index of refraction of the bubble is greater than that of the air, then it'll change phase, it inverts. If it is less than that, then it will not change phase. So in the case of a bubble, where using this illustration, N1 would be air, and N2 would be the soap bubble, and N3 would be air again, then the light coming in for ray number 1 would change phase, and then the light coming in at surface number 2 for N2 wouldn't change phase because N3 is air, which is less than the index of refraction of the bubble. So to find the thickness of the film, you would use one of these two equations. And so if the two waves are in phase, you use the top equation. And if the two waves are out of phase, or one of them flipped and one didn't, then you use the second equation. So here's an example with a bubble. You've got a soap bubble that's 1 nanometer thick, and if you light it with white light perpendicular to the surface, what wavelength is most constructively reflected? At the top, because air has a lower index of refraction than the bubble, you're going to get a phase shift. But because the bubble has a greater index of refraction than the air, at that second surface, there's not a phase shift. And so you would use the equation that I've shown there with the wavelength over 2. Plug everything in, and you end up with 532 nanometers. One of the applications of interference is going to be the Michelson interferometer. It's used a lot in all kinds of industries, chemistry and semiconductor, to measure wavelength of light, refractive indexes, and small changes in length. So you would use it to measure the thickness of thin films. So what really is happening is the light comes from the laser and then it's split at that mirror. And half of it goes to M1, mirror number 1, which is a movable mirror, and the other half goes to a fixed mirror. And they both reflect back and then go to some sort of sensor. And in the illustration that's shown, it shows an eye. But you end up with a fringe pattern that you're looking at from the interference. And moving that mirror causes the fringe pattern to change. And when you move the mirror, those fringes actually look like they're moving outward and replacing themselves in the middle. And if you move the distance of a half wavelength, if you look at that, each one of those bright ones is a peak and the dark line is a trough. If you move a half wavelength, then the fringe moves to the position of the next fringe. And so you would use this in conjunction with this equation here. The change in distance is equal to m, which is the number of fringes, times the wavelength over 2, to find the thickness of whatever it is you're measuring. The distance the mirror moved, the wavelength of light, and you would set it up appropriately. All right, good luck. Bye-bye.